So, under the types of reactions we started 3 types of addition reaction, that is electrophilic addition in alkenes and nucleophilic addition in aldehydes and ketone, and free radical addition again in alkenes, but catalyzed in presence of peroxide catalyst, that free radical addition taking place. Now, similar to the addition, we have a substitution also classified into 3 types. In the substitution, one group is coming in, another group is going out. So, here there is no 2 coming groups, only one is coming, one is going. So, going I am not interested, but incoming group, based on the incoming group, if incoming group is electrophile, I call it as a electrophilic substitution reaction. If a nucleophile coming, nucleophilic substitution. Similarly, free radical substitution. First, let us take the electrophilic substitution reaction. This reaction you can abbreviate as a ESR, but substitution is the main reaction. So, therefore, in many books it is given the notation substitution started by electrophile, therefore, SE. Some books also say especially the reaction is in the aromatic compound, therefore, ARSE, that is aromatic the electrophilic substitution, aromatic electrophilic substitution. Electrophilic substitution on aliphatic carbon, like in the anion reactions we find, but basically the electrophilic substitution means aromatic compounds we take, therefore, you may not use AR every time, but it is clear, nothing wrong to say aromatic electrophilic, that is substitution with electrophile, aromatic substitution with electrophile. Now, the example, the benzene and the all aromatic compounds show this type of the characteristic reaction, all aromatic compounds. The skeleton reaction may be shown like this. When benzene is treated with let us say chlorine, in presence of a catalyst like some anhydrous ferric chloride is taken and heated for some time. So, we are getting a 1 chlorine introduced into the benzene, that is we have 6 benzenes all around this benzene. One of the hydrogen is replaced by the chlorine and the remaining 5 hydrogens will be like that, but the hydrogen which is removed and the Cl goes out as a HCl. So, this is you call it as a byproduct now. So, the benzene when treated with chlorine in presence of ferric chloride, it gives a chlorobenzene plus HCl. This is the one of the suitable or the simple example for the electrophilic substitution reaction, in which the reaction, to study in detail, we divide this reaction in 3 different paragraphs or parts. So, let us call in the part 1. In the part 1, I am showing how the electrophile is generated. So, formation of electrophile I am showing, formation of electrophile. Electrophile, how it is formed. When the chlorine molecule is reacting with anhydrous ferric chloride, in fact, in the market what we get ferric chloride is not anhydrous, it is hydrated, or ferric chloride dissolved in water called aqueous solution, or hydrated ferric chloride is not useful, because in this reaction what is happening is the ferric chloride takes the Cl minus temporarily, forms into FeCl4 minus anion and the Cl plus. The Cl plus and the Cl minus will have a loose bonding. So, this Cl plus is called the reagent. In fact, that is called a chloronium ion. Chloronium ion, that is what our electrophile. So, what is the electrophile in this reaction means? It is not Cl2 molecule, it is Cl plus, that is what electrophile. Even without ferric chloride also the reaction takes place. It is the general statement that the catalyst will not start the reaction, that means without this also reaction taking place, but When I add ferric chloride, the reaction will become easy. Then I have a duty how it makes easy, what is the exact rule or the participation. So, ferric chloride holds, it is a Lewis acid, it has a vacant orbital, so electrons it can take electrophile. So, it holds the Cl minus temporarily, so that the Cl plus is released. That Cl plus, instead of molecule getting and coming and breaking into plus minus, ready made plus if it is there, that will attack in a better way. So, the second part, this is the main crucial part, it is the main product formation of the product. So, the main product, that is chlorobenzene, how it is coming, in which I am using the just 4 structures I am using. First structure is just benzene only, right. The last one is chlorobenzene, only in between 2 structures I am going to write, which are having some placement for the discussion. So, the first you write the chlorine on the arrow and see that it is understood that as the chlorine is moving closer and closer, it is a plus. Again the benzene also considered as electron rich. How can you say it is electron rich? Means the loose bonds, that is pi bonded electrons, in fact they are delocalizing also on the benzene, going on rotating and creating a stability to the molecule. That is, when a reagent is added, before attacking the reagent, electrons are moving. So, static double bonds at a local place, double bond is there, reagent attacks in a better way. But when they are moving, or you call delocalized double bonds are there, reagent will not able to attack, because it is, where is exactly double bond is, don't know. So, therefore, attacking will become difficult. So, such a type of double bonds we call delocalized double bonds. So, here there is a delocalized double bond. So, delocalized electron cloud is there. So, that cloud, and it is a negatively charged and it is positive. Therefore, as the chlorine comes closer and closer, and the benzene undergoing the polarization. So, this step is not attacking, it is called polarization. So, I do not consider this is the step 1, just is coming closer and this is undergoing polarization. And with the electron cloud also it makes a bond, that is called pi bond I discussed, and this pi bond will be, in a normal case we cannot isolate and demonstrate it or show it. But in a case where a strong electron donating group and a strong withdrawing group are a stable electrophile, if it is there, you can show that a pi complex also. Now, as the Cl plus comes closer and closer, total bond becomes into minus and plus. So, on the one of the carbon you find a minus charge in this carbon. So, there is a hydrogen. In this carbon also there is a hydrogen, but a plus charge is formed. This opening of the pi bond will never takes place generally in absence of the Cl plus. Polarization may lead, but not totally into plus minus. This is in fact unstable in fact, but this takes place when the chlorine comes very close. I am sure that the chlorine plus only attacks, the pi bond opens and it undergoes some destabilization even, and during that process now the Cl plus attacks. This is called what? Step 1. So, in the step 1 Cl plus attacking, now we have a fundamental discussion, will the minus attacks on the plus or plus attacks on the minus? In general we say electrophile attacks, but electrophile, because we are saying it is a small one, this is the bigger one, the small one with available kinetic energy runs fast, so attacks, that is meaningful also. Electrophile generally attacks on the compound, this is called substrate on which attacks, reagent attacks. So, nothing wrong to understand, Cl plus attacks, but from which side to which side electrons are flowing? Minus 2 plus. Therefore, it is also right to show that the anion is attacking on the cation, because here there is some electrons, there is nothing is there, positive means no electrons. So, something flows into nothing is the most correct in fact. So, therefore, show that arrow, that to arrow having the 2 sides hooks, that shows a movement of 2 electrons. When I use an arrow with only one sided hook, I said 1 electron movement. So, a curved arrow means a movement of 2 electrons. So, here also a pi bonded electron shifted to the corner. The straight lines shows This is just like a making equalized mathematical equations gives rise to the meaning is here. But this a curved arrow, never show a straight line, use a small curve or S shape, something like that, but big loop, but it should be very clear where from you are starting, where you are ending. So, a bond comes between the carbon and the Cl. So, after step 1, what get you call as a intermediate species. So, Cl is attacked, and the next carbon, however, we have a positive charge, right. So, other 2 bonds are intact. Now, this is called what? Intermediate species. Intermediate species, I say. So, intermediate species again a carbocation. Now, under what condition the carbocation is stabilized? For example, if there is a electron donating group is there, just like a methyl group or a mesomeric effect showing amino group or a chlorine or a OH groups, that carbocation is stabilized. Therefore, any group donating group at this carbon, so substitution takes place side by justified, or at para ortho or para at ortho, if electron donating groups or reaction takes place, that is again we have a discussion later, we will see that. But right now a carbocation is now allowed to attack either by the minus. So, we have now 2 chances. A Cl minus is there with ferrichloride, that minus may attack here, but generally will not take place. That type of step will never take place. If the Cl minus is added, it will become only 2 pi bonds in the ring, is a resonance will takes place, but not the cyclic conjugated planar with set number of electrons. Huckel theory shows that most stabilization feature, that aromaticity is not there in the molecule. So, therefore, in order to get that aromatic nature, the hydrogen is dropped and the 2 electrons present in that CH bond will be given to this CC bond. So, that again a pi bond, that is 3 pi bonds are retained back. The 2 are intact, the third one again formed. The hydrogen, however, detached and expelled out as a H plus. So, in the place of the that is this hydrogen only, Cl has come. So, a product and a H plus is formed. This is the step 2 reaction. So, as I said in the second part, it is not the steps I am saying, this is part 1. In the first part I said how electrophile is generated. The second part I said how the generated electrophile attacks on the compound, and then how the step 1 is taking place, intermediate species carbocation, then step 2, that is H is dropped out. So, minus of H plus, in fact you will get this the chlorobenzene product is formed. That H plus I am continuing to show the another part which is not important for the mechanism part, but still the H plus where it goes, the H plus and the Cl minus which is held with the ferric chloride reacts, that is formation of what I am showing, formation of a byproduct, that is a HCl formation, or the formation of the catalyst also you can say. The catalyst formation also, nothing wrong to say. In the same step I am showing that the H plus reacts with the FeCl4 minus, and the 1 Cl will be given here. So, on that the Cl and the H forms into HCl, that is your byproduct. Again ferric chloride is generated back with the vacant orbital. So, the ferric chloride, that is the catalyst formation. So, the role of catalyst is shown and how the byproduct is formed is shown. And so, never say electrophilic substitution reaction has 3 steps. These are not the steps. Actual step is this only. The electrophile attacking on the compound, intermediate, and the H plus is going out. In the same place Cl has accommodated. So, it is a substitution or replacement. First attacking, that is electrophile coming, and however electrophile only going out. But what is going out is not the criteria for the classification. What is incoming group, that is Cl plus coming. So, therefore, it is called electrophilic substitution. Here, if a Cl minus coming to forward to have a substitution, the benzene is repelling that. So, therefore, only electrophiles are allowed to attack on the benzene, the reaction takes. So, the more the electron density, the reaction will become fast. Like for example, there is a OH group. OH through the mesomeric effect in the ring, the electron density is found to be increased, therefore rate of reaction increases. Because electrophile is attacking, so the more the electrons, the reaction will be. If you have a nitro group, the ring electron density is decreased, so the electrophile will have a deficient, that is difficulty to attack. So whenever activating, that is electron donating groups are there, reaction will become fast. Such groups we call electron, that is donating groups, also called ring activating toward this electrophilic substitution. Or electron withdrawing groups like nitro, aldehyde, cyanide, sulfur and so on, they withdraw the electrons from the ring to show the resonance, so or to the inductive effect. Such compounds will have a rate of reaction decreases, because attacking species is electrophile. More the electron density, readily will attack. Similar the way that is attacking groups also. Attacking, that is donating groups, if should be ortho, para and ortho, then the formed carbocation here will be stabilized. This won't be here always, the double bond will go there, positive charge may come here. Therefore, if electron donating group at para or at ortho, if it is there also, reaction takes place. That means with reference to the electron donating group, the substitution takes place at ortho and para is also justified the other way. So this is what the mechanism of the electrophilic substitution. Once 2-3 times if you write and then perfect this mechanism, we have a huge number of similar very close reaction, that is Friedel-Crafts alkylations, Friedel-Crafts acylation, the nitration, sulfonation, all these reactions follow the same footsteps of this particular reaction. In every that is chapter, one characteristic reaction minimum will be there, and such a reaction, if you master it, most of that reactions of that fundamental reactions of that chapter will be following the same footsteps of that reaction.